Imagine, for a moment, that it is a Tuesday.
Just a normal Tuesday.
A standard, unremarkable Tuesday in the, well, let's say the near future.
Right.
You're going about your morning routine. Maybe you're brewing that second cup of coffee, looking for your keys, scrolling through emails.
Sitting in traffic.
Exactly, sitting in traffic. The sun is shining, the seasons are turning on schedule, and the world feels steady.
It's the illusion of permanence. We rely on it, you know.
How so?
We build our entire psychological framework on the idea that the ground beneath our feet and the sky above our heads are, well, that they're immutable constants.
That tomorrow will be fundamentally like today.
Precisely.
Okay, so let's shift our perspective. Far away from that Tuesday commute, at a remote observatory high in the Atacama Desert, where the air is thin and cold.
Or maybe on an orbital station, something trailing Earth, like a successor to the James Webb Space Telescope.
Right, and the astronomers there are looking at data that simply doesn't make sense.
It's an anomaly.
But they aren't seeing a new object. They're seeing a flash of light or a supernova or a comet with some brilliant tail. They are seeing nothing.
Or, to be more precise, they're seeing the distinct, mathematically undeniable gravitational signature of something massive.
A ghost in the data.
A ghost is the perfect word for it, yes.
The sensors, gravitational wave detectors, astrometric mappers, they indicate an object with, say, the mass of 10 suns, and it's moving through the outer edges of our solar system.
Tearing through the Oort Cloud.
But when they point the optical telescopes at those coordinates, when they look for the source of this immense gravity,
There's just empty space.
no planet, no asteroid, no rogue star.
It's a void where all the laws of physics say a massive object absolutely must be.
And that is the moment the realization hits.
The silence in that control room would be deafening.
It would be.
It would be the kind of silence that marks a before and an after in human history.
Because if an object has the mass of 10 suns, but emits no light, reflects no light, and absorbs no light,
There's only one thing it can be.
the invisible intruder.
A black hole.
Specifically, a stellar mass black hole. A rogue remnant of a dead star just wandering the galaxy.
And it has just entered our solar system on what's called a hyperbolic trajectory, meaning it's not staying, it's just passing through.
Now, I want to pause here for a second because this sounds like a movie plot.
It does.
It sounds like the setup for a summer blockbuster where a team of rugged heroes goes up to, I don't know, drill into the thing.
Right.
But we aren't talking about science fiction today. We're not talking about Hollywood exaggeration. Today, we are going on a deep dive into this specific, well, this nightmare scenario.
And we're going to strip away the myths.
And look at the rigorous astrophysics of what would actually happen.
Yes. We have to use the laws of general relativity, orbital mechanics, and thermodynamics to simulate this. It's a very real, albeit, statistically very rare cosmic possibility.
So this is a stress test.
A stress test for our understanding of the universe.
Exactly. The mission today, then, is to answer the existential questions that would immediately flood the minds of those astronomers.
And everyone else soon after.
What would we see first? Would we have time to prepare? Months? Years? And the biggest question of all.
Would Earth survive the gravitational dance that follows?
It is the ultimate question of celestial mechanics, isn't it?
It is. Can a stable, predictable system survive the introduction of an agent of pure chaos?
So settle in. We're going to establish our Eclipse yard tone here. We'll be calm, authoritative, but we have to face the physics head on.
Okay.
Let's unpack the nature of this invisible intruder.
To really understand the threat, we first have to rigorously define the object itself. I think when most people hear black hole, they have a very specific image in their minds.
Oh, yeah. The monster. The one at the center of our galaxy.
Sagittarius A.
The one from those famous Event Horizon Telescope photographs.
The giant glowing donut of doom.
That's the one.
Exactly. But that is a supermassive black hole. It contains millions, sometimes billions, of solar masses.
It's the anchor around which our entire galaxy rotates.
It is. And if something like Sagittarius A star were to, somehow enter our solar system...
We wouldn't be having this conversation.
No, we absolutely would not. The tidal forces alone would tear the solar system apart before we even knew what was happening. We'd be gone before the light from the event even reached our eyes.
Right, so that's a galaxy under, that's not our scenario.
No.
We are talking about a stellar mass black hole. The name implies the size of a star, but let's break that down. What's the distinction?
Well, a stellar mass black hole is quite literally the corpse of a massive star.
A dead star.
A dead star. According to our stellar physics databases, these objects are born when a star with more than, say, 20 times the mass of our sun runs out of fuel.
So it's the end of a life cycle.
It is.
Yeah.
A star is fundamentally a balancing act. You have gravity, which wants to crush it inward.
And then you have the nuclear fusion in the core pushing outward.
Right. And equilibrium. But when the fuel for that fusion runs out, the outward pressure just vanishes.
And gravity wins.
Gravity always wins in the end. The core collapses under its own immense weight in a fraction of a second.
And that collapse is what triggers a supernova.
It's so violent it triggers a supernova explosion, yes. It blows off the outer layers of the star in this incredible celestial firework.
But the core remains.
The core keeps falling inward. If that remaining core is heavy enough, and the threshold is about 3 times the mass of our sun, nothing in the known universe can stop the collapse.
Not even atomic forces.
Nothing. Not electron degeneracy pressure, not neutron degeneracy pressure. Those forces hold up white dwarfs and neutron stars, but here they're overwhelmed.
So it just keeps collapsing.
It collapses to a point of theoretically infinite density.
The singularity.
The singularity. And surrounding that theoretical point is the event horizon. So for our scenario, we're talking about an object that's maybe 5 to 10 times the mass of our sun.
Let's stick with 10 for the sake of the numbers. 10 solar masses.
Okay. 10 solar masses.
So it's heavy. 10 times the sun is a significant amount of gravity. But how big is it physically? If we could see it, are we talking about the size of Jupiter? The size of the Earth?
This is where the anatomy of the voyage gets fascinating and honestly a little disturbing.
Okay.
We have to look at something called the Schwarzschild radius.
The Schwarzschild radius. Let's unpack that formula.
The formula is relatively simple. It's R sub S equals 2 gm over c squared.
Okay. What do those letters mean?
R sub S is the radius we're looking for. G is the gravitational constant, which is just a number that makes the math work. M is the mass of the object.
So in our case, 10 times the sun's mass.
Right. And c is the speed of light.
And the speed of light is, what, about 300,000 kilometers per second?
Roughly, yes. And it's squared in the denominator of that equation.
So you have a huge number on the bottom of the fraction.
A ridiculously huge number. Which tells you that you need an incredible amount of mass, m, in a tiny, tiny space to get a significant radius, to trap light.
Let's run the numbers then to make this concrete. If you took our sun, which is huge, over 1 million kilometers across, and you could somehow crush it down into a black hole, how big would its Schwarzschild radius be?
About 3 kilometers.
Wait, say that again?
A radius of 3 kilometers.
3 kilometers. That's it.
That's it. A diameter of 6 kilometers. You could, walk across it in an hour if the gravity wouldn't instantly crush you into a stream of atoms.
That's stunning. So applying that to our intruder, if it has the mass of 10 suns...
Well, the relationship is linear, so you just multiply by 10. We're talking about an object with a radius of roughly 30 kilometers.
A diameter of 60 kilometers.
60 kilometers, about 37 miles.
That is tiny.
It's a city-sized object. Imagine something the size of, say, the London metro area, or the beltway around Washington, D.C.
Or a small state like Rhode Island.
A good comparison.
Yeah.
But inside that small circle, you have the gravitational pull of 10 stars, 10 suns.
That is nearly impossible to wrap your head around. A city-sized object that outweighs almost the entire solar system.
It's like a lead bearing dropping through a cloud of steam. Yeah. The difference in density is just astronomical.
Okay. Now, before we get into the destruction part of this, I want to clear up a really common misconception.
I think I know where you're going with this.
The vacuum cleaner myth.
Yes.
I think a lot of us have this idea that black holes just inhale the universe, that they have some special force that sucks everything in.
It's a pervasive myth, and it's really, really important to correct it if we want to understand the actual danger here. Black holes do not suck.
They don't.
No. They obey the exact same laws of gravity as stars or planets. Gravity, according to Newton and later refined by Einstein, depends on 2 things.
Mass and distance.
Mass and distance, that's it.
Yeah.
It does not care what the object is made of or how dense it is. The gravitational field is determined by the mass.
Okay, so let's use the classic thought experiment to prove this. The sun replacement scenario. If we snapped our fingers right now, hypothetically, and replaced our sun with a black hole of the exact same mass, 1 solar mass, what happens to Earth's orbit?
Absolutely nothing.
Nothing. We don't spiral in. We don't get sucked into the void.
Nope. Earth would continue to orbit that 1 solar mass black hole exactly as it orbits the sun today.
Why?
Because we're 150 million kilometers away, 1 astronomical unit. At this distance, the mass is the same, So the gravitational pull is identical. The curvature of space-time where Earth sits would be completely unchanged.
That is such a crucial distinction. We would still be in a stable orbit
Now, obviously, things would get very bad for us very quickly.
because of that light and heat would go out.
We would freeze to death in the dark. But gravitationally, we would be fine. The danger of a black hole isn't some magical suction power.
So what is it?
The danger is simply that it allows you to get much, much closer to that central mass than a normal star would allow.
Ah, I see.
You can get within 30 kilometers of the center of mass of our 10 solar mass intruder. You can't do that with the sun. Its surface is almost 700,000 kilometers from its center. You'd be deep inside it.
So the danger of our rogue black hole isn't that it sucks, it's that it disrupts.
It's a gravitational bully.
It's a massive object moving at high speed through a delicate, balanced system.
That's the threat. Exactly.
Okay, so we've established the foundation. We have a 10 solar mass object, 60 kilometers across, moving silently through the dark. Let's start the simulation. Section 2. The entry. Where do we first spot this thing?
So we enter scenario A, the outer pass. The black hole is moving through the interstellar medium, and it's approaching the Oort Cloud.
And the Oort Cloud is what exactly?
It's a vast spherical shell of icy debris that surrounds our solar system. It extends nearly a light year out from the sun. It's the source of our long-period comets.
And the first sign wouldn't be the movement of planets.
No, it'd be much more subtle. The first sign would be light.
Light. But you just said it's invisible.
The object itself is invisible, but the space behind it isn't. As this massive object moves against the backdrop of the galaxy, its gravity is so intense that it acts as a lens.
It bends the light from the stars behind it.
Yes, gravitational lensing. This is one of the core predictions of general relativity.
And we've seen this happen, right? This isn't just theory.
Oh, absolutely. We use it all the time in astronomy to study distant galaxies. Massive objects curve space-time, and light has to follow the curvature of space.
So an astronomer looking at a familiar star field would see a distortion.
Exactly. They might see a star momentarily brighten as the black hole's gravity focuses its light toward Earth like a magnifying glass.
Or it could shift position.
It could tear to shift position, or even split into duplicate images. Sometimes you see what's called an Einstein cross or an Einstein ring, where the light is smeared out into a circle.
So it would look like a flaw in a glass lens moving across the sky.
That's a haunting image, a perfect way to put it. Just a ripple in the dark, a wandering distortion.
And that gives us its trajectory.
That gives us its trajectory, its speed, and we can calculate its mass based on how much it bends the light.
And that's when the panic sets in.
That's when the panic sets in, because we realize it's heading inward.
And as it gets closer, as it actually punches through the Oort Cloud and then the Kuiper Belt.
Then the physical effects begin. Think of the solar system's outer edge as this delicate, fluffy halo of ice and rock.
Okay.
The black hole passing through it is like throwing a bowling ball into a pile of marbles.
It's scattering everything.
It's a massive gravitational perturbation.
Yeah.
It destabilizes the orbits of millions, maybe billions, of comets and asteroids. Objects that have been quietly orbiting for 4.5 billion years are suddenly kicked into new, chaotic paths.
So long before the black hole itself gets anywhere near Earth.
We would see a reign of terror.
A reign of terror.
The statistical probability of major impact events on Earth would skyrocket. We're not just worried about the one big object anymore, we're worried about the shotgun blast of debris it flings inward.
A swarm of comets heading for the inner solar system.
It would be an age of impacts unlike anything humanity has ever seen.
So the preamble to the main event is an asteroid bombardment. Great. That sets the stakes.
It does.
But let's get to the main event. Scenario C. The rogue close encounter. The black hole enters the planetary region. It crosses the orbit of Neptune, then Uranus. What happens to the delicate balance of our solar system?
This is where we run into the famous three-body problem.
I've heard of that. It's famously unsolvable, right?
It is, analytically. And in this case, it's an n-body problem, which is even worse. Our solar system is stable because the sun is the dominant gravitational anchor. It holds 99.8% of the mass of the entire system.
It's the boss.
It's the boss. The planets are in this delicate, predictable resonance. It's like a well-oiled clock.
And we are introducing a sledgehammer to the clockwork.
A 10 solar mass sledgehammer. When you introduce a second gravitational anchor, remember, this thing is 10 times heavier than the sun. You destabilize the entire architecture.
The sun is no longer the undisputed boss.
Exactly. It's not just the planets orbiting the sun anymore. The planets and the sun itself are now orbiting the common center of mass between the sun and the black hole.
They're getting pulled between two masters.
Precisely. And so orbits stop being neat ellipses. They become chaotic, hyperbolic, or highly eccentric.
What does that mean for the planets?
Depending on their trajectory, the black hole could pull Jupiter out of its stable orbit. And if Jupiter moves, its own immense gravity acts as a lever on everything else in the system.
So if Jupiter shifts, it could throw the inner planets, Earth included, into chaos.
Complete chaos. It could fling Mars into the asteroid belt. It could push Venus closer to the sun.
And for Earth, we get eaten, swallowed.
Well, here's the counterintuitive part. That's actually statistically unlikely.
What? How is that possible?
Think about the scale. The event horizon is only 60 kilometers across. Space is enormous. The target for consumption is incredibly small.
So a direct hit is unlikely.
Vanishingly unlikely. The most probable outcome for Earth in a close encounter isn't being swallowed, it's being ejected.
Ejected, like kicked out of the club.
Exactly. Gravity works like a slingshot. We use this in space travel all the time. We call them gravity assists.
Right. We fly a probe near Jupiter to steal some of its orbital momentum and speed up.
Now, imagine Earth is the probe, and the 10 solar mass black hole is the massive object. If Earth passes close to the black hole, but not directly into the event horizon, the transfer of momentum would be immense.
Would accelerate us.
It would almost certainly accelerate Earth beyond the sun's escape velocity.
Because we'd be ripped away from our star.
And flung into interstellar space. We would become a rogue planet drifting alone in the dark.
That is arguably worse than being eaten. It's a much slower death.
It is.
But before we get to the freezing to death part, is there any scenario where this invisible object becomes visible? Does it ever light up?
Yes. This is the fire in the sky scenario.
Okay.
If the black hole's trajectory takes it through a gas giant like Saturn or Jupiter, or if it grazes the outer atmosphere of the sun, it will feed.
And feeding means matter is falling into it.
Right. But matter doesn't just fall straight in. It has angular momentum.
So it spirals.
It spirals. It forms what we call an accretion disk, a whirlpool of superheated gas and plasma spinning around the black hole at near the speed of light.
Like water circling a drain, but the water is plasma and it's moving at relativistic speeds.
Exactly. And the friction in that disk is unbelievable. It converts gravitational potential energy into heat and light with incredible efficiency.
How hot does it get?
The disk heats up to millions of degrees. Suddenly, the invisible intruder becomes the brightest object in our sky. It would easily outshine the sun.
And that's not just visible light, is it? We aren't just talking about a really bright light bulb.
No, not at all. It's glowing in the high-energy end of the spectrum, X-rays and gamma rays. A black hole with an active accretion disk is a massive radiation hazard for the entire solar system.
And what about the jets? I've seen the illustrations of black holes with these huge beams of light shooting out the poles.
Relativistic jets. As matter swirls in, powerful magnetic fields get twisted up and they channel some of that plasma, blasting it out from the poles at nearly the speed of light.
So if Earth were to pass through the path of one of those jets...
It's a death ray.
Literally.
Effectively, yes. A blast of high-energy particles and radiation. Our ozone layer would be shredded in an instant. The atmosphere could be stripped away or at the very least sterilized. It's the death by radiation scenario.
Okay, so we have the asteroid rain, the radiation death beam, and the solar system ejection. 3 very unpleasant possibilities.
To put it mildly.
Let's assume we avoid the jets. Let's assume we avoid a direct impact with the comets. Let's assume we face the rogue Earth scenario. This feels like the most psychologically terrifying one.
I agree. It forces us to confront the absolute fragility of our biosphere.
Let's play that out then. Section 3. Human and civilizational impact. The black hole has swung by. It hasn't hit us, but its gravity has catapulted Earth out of the solar system. We're now drifting away from the sun at thousands of kilometers per second. What is the timeline of the end?
It is fundamentally the timeline of cooling. Phase 1 happens in days or weeks.
That fast.
That fast. As we distance ourselves from the sun, the light fades. It goes from a bright yellow disk to a small, brilliant star, and then just another point of light in the distant sky.
And without sunlight.
Photosynthesis stops almost immediately.
The foundation of the food chain.
It's the collapse of the foundational energy source for almost all complex life on Earth. Plants die first, the great forests of the world turn brown and wither.
Then the herbivore star.
And then the carnivores. The entire surface biosphere collapses from the bottom up.
We would still have our own energy sources, though. Fossil fuels, nuclear power. We could keep the lights on in our cities for a while.
We could keep the artificial lights on, yes, but we couldn't heat the entire atmosphere. The planet is losing heat to the 3 Kelvin background of empty space, and there's no energy coming in to replace it.
So the global temperature plummets.
Within months, this is phase 2, the oceans begin to freeze. Not just the ice caps expanding. The surface of the Atlantic, the Pacific, the Indian Ocean.
It would start with sea ice extending from the poles until it finally meets at the equator.
Yes, a global ice sheet. Earth would become a snowball. The oceans would be covered in a thick shell of ice, maybe kilometers thick eventually.
Could life survive under the ice?
For a time. You might have ecosystems huddled around deep-sea hydrothermal vents, feeding off the planet's internal heat. But the surface becomes completely uninhabitable.
And then it gets worse.
Then the true end of the surface world comes. Atmospheric collapse.
Atmospheric collapse. That sounds distinct from just, it gets cold. What does that mean physically?
Well, we think of air as a gas. But any gas will turn into a liquid or a solid if you get it cold enough.
Right.
As temperatures on the surface drop toward absolute zero, the gases in our air begin to change state. First, the water vapor freezes out entirely. The air becomes bone dry. Then the carbon dioxide turns to dry ice and falls as snow.
And then the main components of our air, nitrogen and oxygen?
Eventually, around minus 196 degrees Celsius, nitrogen condenses. Then oxygen, a bit colder. The very air we breathe would first turn into a liquid rain.
Liquid oxygen raining from the sky.
And then it would freeze into solid ice on the ground.
So it would literally snow the sky.
Yes, the sky would fall. The atmosphere, which protects us from cosmic radiation and meteors, and which, allows us to breathe, would lie in frozen drifts on the surface of the planet.
Earth would become a frozen, airless rock drifting in the void, a naked planet.
That's the end state. A silent white tomb.
Is that it then? Is that the end of humanity? Or do we have survival strategies? We're a pretty stubborn species.
Humans are incredibly stubborn, and we are technological. If we had enough warning, and that's a big if, say, a few years as the black hole approaches.
What would we do?
We would attempt an underground migration.
We go down.
We have to. We can't stay on the surface. We would have to dig deep, kilometers down into the Earth's crust.
Why so deep? Why not just heavily insulated bunkers on the surface?
Energy. Without the sun, we need a new, permanent source of heat. The core of the Earth is still incredibly hot, thousands of degrees Celsius.
The planet's own internal heat.
Right. It acts as a giant nuclear battery powered by the slow decay of radioactive isotopes like uranium and thorium that were trapped here when the planet formed. That heat radiates upward.
Geothermal energy.
Exactly. If you go deep enough, the ambient temperature of the rock is warm enough to live in. We could build self-sustaining habitats powered by geothermal plants. We'd be tapping into the Earth's own blood heat to survive.
So we become a subterranean species. We huddle around volcanic vents like deep-sea bacteria.
It's a very good analogy. All our surface energy sources are gone. Solar power is gone. Wind is gone because the atmosphere is frozen. Hydro is gone.
So it's all geothermal and nuclear.
Entirely. We would rely on nuclear fission and hopefully by then, fusion alongside geothermal. Our civilization would have to contract enormously.
What do you mean by contract?
The carrying capacity of the planet would plummet. We currently strive to become a Type 1 civilization, one that harnesses the full energy output of its planet. We would instantly revert to bare-bones survival mode. The population would drop from 8 billion to maybe a few million, if we're lucky.
It would be the ultimate bottleneck event in human history.
It would.
And psychologically, what does it do to us? To lose the sky, to lose the concept of day and night, the seasons?
It changes what it means to be human. We are creatures of the circadian rhythm, evolved under a sun and a moon. Without them, we would be living in an eternal, artificial now. We'd have to invent our own time, our own cycles. The psychological toll would be immense.
Let's talk about mitigation for a second. Could we stop it? Or could we escape it? We have the Interstellar Civilization database here in our notes. What are the options?
The options are bleak, to be honest.
Chemical rockets, the kind we use now.
Useless for moving large populations. They're far too inefficient. You can't evacuate a planet with them.
What about more advanced propulsion? Ion drives or nuclear pulse propulsion? That Project Orion concept with the atomic bombs.
Better. Much better. But you're still talking about building arcs.
Generational ships.
Yes. But where do you go? The nearest star is Proxima Centauri, over 4 light years away. Even with our best theoretical nuclear engines, that's a journey of centuries, maybe millennia.
And you'd be launching these arcs from a planet that is actively dying, freezing over, with an atmosphere that's literally raining down.
The logistics are a nightmare.
And we can't just move the Earth. I know there are these mega engineering concepts like Dyson swarms or stellar engines, Shkadov thrusters.
We lack the energy capacity by many, many orders of magnitude. Pushing a planet out of the way of a 10 solar mass object, that's a Type 2 civilization capability, harnessing the power of a star. We are barely a Type 2.7.
So we'd be spectators to our own eviction.
We could watch it happen. We could calculate it happening with incredible precision, but we couldn't stop it.
Okay, let's go deeper. Let's zoom all the way in. We've talked about the planet. But what if? What if you, personally, fell into one of these things?
Ah,
Section 4, Deep Physics. Let's talk about the specific horror of interacting with a stellar mass black hole up close.
this is where the physics gets very strange and very violent. We have to talk about tidal forces.
No, a tidal force is just gravity, isn't it?
Essentially, yes, but it's more specific. It's the gradient of gravity. It's the difference in the gravitational pull between two different points.
So if you're falling feet first toward a black hole,
Your feet are closer to the singularity than your head is.
right, and gravity gets stronger the closer you are, so the pull on your feet is stronger than the pull on your head.
Exactly. On Earth, we don't notice this because the difference is microscopic. The Earth's radius is 6,400 kilometers. So the difference in distance between your head and your feet is negligible. The gradient is gentle.
But with a black hole.
Black holes are different. Tidal forces grow much, much faster than the simple gravitational attraction. They obey an inverse cube law, not an inverse square law.
Yeah.
So as you get closer, the difference grows exponentially.
And here's the paradox you mentioned in the notes, which I found fascinating. A smaller stellar mass black hole is actually more dangerous to your body than a supermassive one.
That's right.
Wait, the smaller one is more dangerous? Why? That feels completely backwards.
It's all about the radius and the steepness of the gravitational cliff. A supermassive black hole is huge. Its event horizon could be the size of a solar system. It's so large that the point of no return is very far from the central singularity.
Okay.
So if you were to fall into a supermassive black hole, you could cross the event horizon while still being alive and intact. The tidal forces at the horizon might be survivable because the slope of gravity is still relatively gradual over the 2-meter lengths of your body.
But with our 10 solar mass intruder,
The event horizon is only 30 kilometers from the center. The gravity is ramping up over mere meters, not millions of kilometers. The cliff face is practically vertical.
so what happens to the human body?
You would undergo spaghettification long before you even reach the event horizon.
Spaghettification. It's such a funny, almost cartoonish word for what must be a horrific process.
It's gruesomely precise. The difference in the gravitational pull between your feet and your head becomes stronger than the molecular bonds holding your flesh and bone together.
So your feet are being pulled so much harder than your head.
That your body is physically stretched.
Like taffy.
Like taffy, yes.
Mhm.
And simultaneously, you're being compressed from the sides. So you would be literally drawn out into a long, thin stream of subatomic particles. You'd be unraveled.
A stream of biological pasta heading for the singularity. Not a great way to go.
Not at all. It is instantaneous biological disassembly.
What about time? We know from Einstein's relativity that gravity affects the flow of time.
Time dilation. Yes, this is one of the most mind-bending aspects of general relativity. Gravity warps space-time. And the more curved space-time is, the slower time flows for an observer inside that curve, relative to someone outside of it.
So if we threw a clock or a probe at the black hole,
If we stood on Earth and we watched a probe fall toward the black hole, we would never actually see it cross the event horizon.
it would just stop.
From our perspective, yes. As it gets closer to the event horizon, the light signals it sends back to us have to climb out of a deeper and deeper gravity well. It takes them longer and longer.
The observer effect.
Right. The light from the probe would get gravitationally redshifted. It would get dimmer and redder, stretching into the infrared, then radio waves. Its motion would appear to slow down until it effectively freezes on the edge of the void, fading into complete invisibility over an infinite amount of time.
But for the probe itself, did time stop?
No. For the probe, time passes normally. It crosses the event horizon and hits the singularity in milliseconds. Its clock is ticking just fine from its own perspective.
But for us, the image of that probe is frozen forever on the event horizon.
A ghost lingering at the door. It's a fundamental disconnect between two frames of reference.
That is deeply haunting. And just to check one last physics concept, Hawking radiation, we hear about black holes evaporating over time. Would that provide any heat for our freezing Earth? Could we huddle around it for warmth?
A great question, but unfortunately, no. Stephen Hawking's brilliant insight was that black holes do radiate energy due to quantum effects at the event horizon.
Right.
But the amount of that radiation is inversely proportional to the black hole's mass. Small black holes radiate a lot. Massive black holes radiate almost nothing.
So a 10 solar mass black hole?
It is incredibly cold. Its effective temperature is just a tiny fraction of a degree above absolute zero. It would take it far, far longer than the current age of the universe for it to evaporate.
So it offers no warmth.
It is a cold, dark engine of pure gravity.
Okay, so we have painted a picture of absolute desolation, a frozen Earth ejected into the dark, or a spaghettified demise for anyone who gets too close. It's heavy. It's terrifying.
It is.
But let's pull back. Let's get some perspective. Section 5, Cosmic Perspective and Probability. How scared should we really be? Do I need to start digging a bunker in my backyard tomorrow?
This is where we can all breathe a collective sigh of relief. This is where the numbers save us. The universe is terrifyingly violent, yes, but is also terrifyingly empty.
The scale of it all.
We have to look at the density of space. The distance to our nearest stellar neighbor, Proxima Centauri, is 4.24 light-years.
And a light year is about 10 trillion kilometers. So we're talking about 40 trillion kilometers.
It's a number so large it's meaningless. It's hard to visualize that kind of empty.
Let's use an analogy.
Okay, let's think of the sun as a grapefruit in New York City.
Okay, a grapefruit in Times Square.
If the sun is a grapefruit in New York, where do you think the next nearest star Proxima Centauri is? Another grapefruit somewhere in, say, New Jersey.
I'm guessing further.
Another grapefruit in San Francisco.
Wow.
That's the scale.
That puts it in perspective. That is a lot of empty continent between just two grapefruits.
An immense amount of nothing. Now, the black hole in our scenario isn't a grapefruit. It's a small marble, a city-sized object.
So to have this disaster, that marble has to randomly roll from San Francisco and pass through the exact tiny space occupied by the New York grapefruit's little neighborhood of planets.
The odds of that marble even hitting the grapefruit in New York are infinitesimally small.
And there are millions of these things, right? Rogue black holes in the Milky Way.
There are. Estimates range from 10 million to a billion. But the galaxy is 100,000 light-years across and 1,000 light-years thick. The volume of space is so vast that two stars directly colliding is an event so rare we struggle to find examples.
So we are far more likely to be hit by a normal asteroid or affected by a gamma ray burst from a distant galaxy or a supervolcano eruption here on Earth.
By many, many orders of magnitude, yes. The danger is real, but the probability is vanishingly small.
It's the empty space defense.
Precisely. Space is mostly nothing.
And briefly, there's a strange connection to dark matter here, isn't there? Some theories suggest that space is actually full of these things.
There is a hypothesis, yes, that some or all of dark matter, the invisible mass we know is holding galaxies together, might be composed of billions of tiny primordial black holes.
Primordial.
Meaning they weren't formed from collapsing stars, but were formed in the ultra-dense conditions of the Big Bang itself.
But they're too small to hurt us.
Exactly. If they exist, they could range from the mass of an asteroid to less than the mass of the moon. They might be passing through our solar system, even through the Earth itself, all the time. But their Schwarzschild radii are microscopic. They wouldn't have the mass to cause the kind of gravitational chaos we've been describing.
They pass through us unnoticed, like neutrinos.
That's the idea. So it's not a threat in the same way.
So we are safe. Statistically speaking, at least we are safe. Which brings us to our final section. Section 6, the philosophical conclusion. Why talk about this? Why spend an hour simulating our own destruction if it's so incredibly unlikely to ever happen?
I think it connects to the anthropic principle and maybe to the idea of gratitude.
Gratitude.
We look at our solar system and it seems boring, doesn't it? The planets move like clockwork. The sun is stable. We take it for granted. We complain about the weather.
Right.
But this stability is a rare, precious calm in an astonishingly chaotic universe. Our very existence depends entirely on this specific, delicate gravitational balance.
It's fragility and luck. We're the masters of the universe. We are just passengers on a very fortunate rock that happens to be in a quiet, cosmic neighborhood.
Exactly. It teaches us a kind of cosmic humility.
Uh-huh.
The black hole in our story isn't evil.
Yeah.
It doesn't hate us. It isn't a monster.
That's just gravity.
It is just gravity and geometry. It reminds us that we are not the main characters of the cosmic story. If a black hole passed through, it would rewrite our history without a second thought, not out of malice, but because the laws of physics demanded it.
It really recontextualizes our problems, doesn't it? We worry about traffic, about the economy, about politics, but really we're all just incredibly lucky that the geometry of space-time hasn't decided to fold in on us today.
And that leads to a different kind of wonder. Instead of fear, maybe the correct response is gratitude. The universe is filled with these monsters, black holes, magnetars, supernovas, gamma ray bursts, and yet here we are.
We have survived in the light.
We have managed to evolve, to build civilizations, to create art, and, to sit here and have this conversation in a universe that is mostly hostile darkness. We are an anomaly of order in a sea of entropy.
So here's the thought we want to leave you with. We explored the physics of destruction not to scare you, but to maybe help you understand the profound value of our current safety. The next time you see the sun come up, remember that it is not guaranteed. It is a gift of orbital mechanics.
Perhaps the real mystery is not whether a black hole could destroy us, but how, in a universe of such violent forces and infinite darkness, we have managed to survive in the light for this long.